We can
Just do that.
probably place it somewhere like that.
We'll see how that turns out.
That should work. Yeah, that should work. Yeah.
No, this is from the projector. I'm just videotaping.
Oh.
Oh.
Oh, we thought it was coming out.
It's got it.
Wait, are we being recorded?
Yeah, so of course you will have to
I'll try to cut
sign
down on the
a whole bunch of
racism.
forms from your parents. No, you've already signed the forms. What the heck? Somewhere. Like,
This is just so my professor can see what I'm doing.
that she was actually. I don't think they're probably going to watch all the videos.
No.
Okay, good, fine.
But there's proof here that it was the presentation was live. And this is the live audience. They're very smart. So
I'm excited.
ask them really deep probing questions. You better not embarrass me.
What I'm going to talk about today is called the Verkeerste-Kroon problem, and we're going to go into it a little bit, but we'll start by defining Verkeerste-Kroon. It is a path between 2 points along which a body can move under gravity in a shorter time than for any other path. So it's the fastest path between 2 points that a mass can move under just gravity. And it comes from the Greek brakistos, which means the shortest, and chronos, which means time. So in 1696, Bernoulli asked a bunch of his mathematician friends if they could solve this problem. He solved it, his brother tried, and his brother solved it. Galileo worked on it later, and Newton was also a big part of this problem. So it was kind of cool to send out a problem to people and prove that you were the smartest. But if you want to give it a try and start thinking about it, the problem is given 2 points A and B in a vertical plane, what is the path traced out by a point acted on only by gravity, which starts at A and reaches B in the shortest time? So the first part of your worksheet is a design your own Verkeerste-Kroon. If you want to imagine that the top arrow on the y-axis is A and the arrow on the right side of the x-axis is B, maybe jot down some ideas, what you think might be the fastest path. Is it the shortest path? Does it matter? Does it have a loop-de-loop in it? Start thinking about that on your own, and then once you have an idea, maybe turn to the person next to you or behind you or in front of you, and chat about what you think would make a fast path.
The ultimate shape of a toboggan rack.
Yes.
The fastest, but not necessarily optimization. It is.
Yeah.
You see?
I like that. So does it go a far distance and then drop down? Does it drop down and then travel horizontally? Is it just the degree angle, a straight line from A to B? Does anyone have any ideas? Who thinks they designed a really fast path? Downward slope and then straightening out.
1 over x squared.
1 over x squared, okay, fitting the type of function to it. Anyone else have an idea? Does anyone think a straight line would be faster? Okay.
It's a possibility I didn't consider.
What I've built in this demonstration, we have the shortest path from A to B. Can you see over there? The straight line behind is the shortest path from A to B, right? And then this is the path that, what was your name? That Andrew mentioned, that dips down a bit and then continues to flatten out and travels horizontally. So any predictions? Who thinks the straight one's faster? Who thinks the curved one's faster? Does anyone want to say why?
We trust him.
Yeah,
Because Andrew said so. They fall by authority.
Okay.
He's the genius.
Yeah.
Pardon?
And also plane flies like that.
Okay.
Like what I've experienced is.
How's that?
Well, like when you see the path, when I go to Korea, it kind of looks like curved, not just like straight.
For what? For an airplane?
Yeah.
Is it about the landing or the roots?
So it's always like this. Maybe it lies
Wait, Robin, you mean the root from?
Yeah, root is
Well, the root's curved because the roof the roof.
Oh, you mean the route that you see on a map?
Yeah, that looks like that because
Oh,
the earth
that's
is
because
curved.
the Earth's, that's because the Earth's circular.
Yeah, that's actually going straight on.
Yeah. But yeah, no, I know what you mean. Yeah, all the routes from here to Asia are great circle routes.
Yeah.
That's what we're gonna find out.
How many
Can I get two
public
volunteers?
sites?
Do you want to volunteer? Yeah. Yeah.
They
Okay.
don't like straight.
And what are your names? Karen and Katie. Okay. Karen, do you want to drop these two balls from the top? And Katie, put one of each hand at the end of each.
You're
track.
the sensor.
Yeah.
Oh, you're the
You're gonna be your
sensor.
sensor. And you're gonna try and drop them
What
at the
is
same time.
That one hit this one on the right.
The curved one?
Yeah.
Did you want to switch and try it
Yeah.
again? Can you see it over there?
Average the results.
Oh yeah, that's what
How much faster? Was it easy to tell or hard to
Yeah,
tell?
it was pretty good though.
Okay, awesome. Thank you.
We should graph this.
You grab it.
Okay. Chris!
I've got a lot of graphs for me.
So a couple of you, I heard a little bit about the curved one is going to accelerate faster right away, even though it has longer to go. So next, if you want to see part 2 of the handout, if you want to draw 2 free body diagrams, one for the straight path and one for the curved path, as if the ball started, or as if the ball was the same, like X displacement. So on the curved graph, the ball is here, and on the straight graph, the ball is here. So in this case, we can discredit or ignore friction. I have 2 really, really soft and fast ball bearings on plastic. So there isn't much friction at all. So other than that, what are the forces acting on the ball? Gravity and normal force. And which one of those is going to make the curved track faster? Gravity? Why gravity? It makes it accelerate, but the force of gravity is the same on both balls,
Oh, okay.
right? Because they both have the same mass.
Well, MG's the same.
Right? So if we look, does everyone have their free body diagrams drawn? Yes. The normal force, which direction is the normal force point? To the surface. That's right. Okay. So these are our 2 free body diagrams. And some of you were mentioning sine theta, right? If you were to break the normal forces into their components, more of this one, of the curved path, is moving it down and to the right, right? In this case, we have quite a bit more normal force that's acting vertically than in this case. Does everybody see that? So that's kind of the instinctive way to talk about why the curved path is faster. But what Bernoulli did was he used a calculus of variations. So you're all in calculus, right?
Yeah.
Everybody? Anybody not? No? So, if you'd like to draw it, yeah, sure. Okay. Use as much space as you'd like. So what we can do by using the calculus of variation is we can define any curve S and find how long it is. So in the case of this straight path, how long is it? How can you find the length? Pythagorean theorem, right? So if we have or with a ruler, that's true. So if we have x and y, I'll take it this way. If we have the change of x and the change in y, it's easy to find the part that is in between, right? Just by Pythagoras theorem. So that's an easy one, but when it comes to the curve, how would you do it then? Calculus.
Yes.
Something about tangent lines. Kind of. So what we're going to do is, it's similar to the straight line. It's easier to use Pythagoras theorem on the straight line because, you know, you can always make a right angle with it. In this one, if you use delta x and delta y, the hypotenuse is almost the hypotenuse, right? It's a little bit curved. So what calculus does is it breaks it into smaller parts so that it, right, so it looks even more straight, right?
Oh, yeah.
If we have just a little triangle, that part looks more like a straight line. So instead of using delta s in calculus, what you use is ds, which is an infinitesimal sized length, so small that when you're using the change in x and the change in y, it looks as if there's a straight line in between. Does that make sense?
Yeah.
So, with a little bit of rearranging, if you'd like to write these steps down, feel free. This is divide both components or factor out a dx squared, right? And then the dx can come out of the radical sign. And does anyone, yeah, so this would be a very, very small length of the curve in terms of what? Right, so small pieces of x, small pieces of y, how the ball might be moving. The next step is what is the velocity in terms of s? Does anyone have a guess? ds dt, exactly. Does everyone follow that? So a very small distance over the very small amount of time. And you were mentioning optimization, so which variable do we want to optimize here? Or minimize in the Brookes system? Time, exactly. So we'll rearrange for time. And we know what ds is in terms of y and x. And all that we have left is v, which we'll go into later. But at this point, what Bernoulli did was he added up the very, very, very small t's and minimized that quantity and got these two equations, parametric equations, which are the equations for cycloid. So Bernoulli and all of his mathematician friends found out that the very, very fastest path between 2 points under gravity is always a cycloid. And they did that mathematically. Have you heard of cycloid before? No?
You guys have done conic sections, right? Ellipses?
Yeah.
Hyperbola?
The optimization.
You do that in optimization?
Okay, have you heard of parametric equations? Okay, so do you see how there's an x equation and a y equation in terms of a third variable, which is theta? That means both of these equations will be like graphing at the same time with the same variable. So if theta were like 1, then there will be an x coordinate and a y coordinate that corresponds to that theta. Does that make sense? So on your calculators, there should be like a parametric function if you want to try that out. And not all it does is graphs two equations at the same time. I think it's under OISD. I can show you after class if you want to, because there are parametric equations is a really easy way to write like quite a few types of shapes and things like that.
You hit that at the end of first year, wouldn't you? Yeah.
I believe so.
So, end of first year calculus.
First year math. So, what a cycloid is, other than that confusing equation, is it's the path traced out by a point on a wheel that's rolling along a horizontal surface. So in an ideal world, this GIF would work on my PowerPoint. But hopefully you can imagine the blue wheel rolling along the green line, and then the point is like a stick of, or like a piece of gum, and it draws out that cycloid. Can you kind of visualize that? So that's the shape, that's the solution to the verticisome problem. And that's the shape that I've made here. This is the very, very fastest track that you could ever get from this point to this point.
I just realized we have one.
Oh, look at that.
Exactly. So it's, put a chalk mark right there, roll the wheel along, starting right from there. Right? So it makes a circle to there, and then it makes another circle to there. Right? So it's just, so you just see something going bump, 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 bump along like that. You had something.
Nice. So yeah, this shape is it like maximizes the initial acceleration with the x displacement, and it's the fastest way to get from A to B under gravity. And another cool property of it is that it takes a ball the same time to fall to the middle of the cycloid, independent of the height that it's dropped from. So if I have a ball and I drop it from here, it will take the same time as if I drop it from here. Does anyone have any ideas of why that might be, just instinctively?
So is this the time to the end, or to the time
To the middle.
to the middle? Okay.
To the middle.
Yeah. So if this is the bottom of the inverted cycloid, then the time that it takes to get to the middle is the same,
As, no matter where you
no
drop it.
matter the height that you start from.
And do you know anything else that works like that? They should.
So, yeah.
Something where the time is the same regardless of where you started from? Yes, good for you, pendulum.
Oh.
Isn't your pendulum the same?
That was
Sounds
the weekend.
familiar.
Yeah, so your pendulum, it's the same idea, isn't it? So the pendulum from there, watch yourself. And then go from there, the time it takes to do its swing is completely independent of how far back I pull. It's really kind of the same idea, isn't it? Because you're starting higher up, so it goes faster, but it's got further to go, right? So what, just while we're here, what factors do change the period of the pendulum? The length. How about the mass? No. Good.
Smart. You pass. So yeah, even if you drop it from higher, it has a longer distance to go, but it will accelerate faster, right? Than from the bottom, where it's has a shorter distance, but will travel slower on average.
So if you start 1 centimeter from the end, you start the other one at the top, they'll both get to the end at the same time. That's pretty cool.
Right? You can try it. Last time it kind of worked. See that?
That worked very well.
Cool.
That's pretty cool.
There are lots of YouTube videos. It's a really common project for people to also visualize this with computer programs. So there's lots of cool cycloid things to watch on the internet, which is what I've done. So the next thing I wanted to go into is analyzing the energy along both paths. This will probably be a review, but what is the initial energy of a ball at rest at the top? MGH.
See how fast they were at?
So good.
It's totally, we just had a grade 11 class this morning. It was kind of.
Right? And so what kind of energy is that?
Potential.
Okay.
Wow, it's like a choir.
So we have U is MGY or MGH, right? And what happens to the potential energy as the ball descends along the ether path? Right, and what's the formula for that?
There's definitely a qualitative difference.
So good. So, and then we have the conservation of energy theorem, which says, go for it.
Yeah, say it, Celine.
Celine.
You're really confused. Right, that's
Pressure's on, Celine.
So all of the initial
No
potential
GH.
energy becomes the final kinetic energy, right? So then what we can do here is solve for that velocity we were missing earlier. And then we would have the arc or the time in terms of everything of y, of dy and dx. So this is also saying that when we compare these two curves, as long as the balls are at the same height, they have the same velocity, right? So we can see maybe here, if one ball is on the straight curve and it's traveled this far, it will only have traveled this far to reach the same velocity. So that's how you can see that this one picks up velocity very, very fast. Do you see that comparison?
Oh, yeah.
So on average, the velocity along this curve is faster, is greater, even though they'll end up at the same final velocity. Does that make sense? Awesome. So that's what I have here. For both curves, at any height, the ball has the same speed for both the cycloid and the chord.
Fantastic.
So good.
So now for some completely different questions. Do you guys have any questions about
Yeah.
physics at university?
Well, so that's all I've prepared, and there's also a little summary box on the bottom of your handout. If you want to jot down one thing that surprised you, one thing you learned, just a one sentence that you want to remember this lesson by.
I can't wait to find out what a parametric equation is.
So, those questions if I just drop the ball, like here, if I just drop the ball.
Well, this is set up for 2 points that are at different x spaces.
Oh,
Yeah, if you really want to get to the bottom fast, just jump.
Last class, what I talked about is if you're walking somewhere, are you going to walk in a straight path or in a cycloid path to get there the fastest?
Certain time.
Oh,
Straight, cycloid?
Cycloid's fast, you're not using the straight or like.
No, they're not cycloids, serpentine.
Straight.
Straight path. Straight path, why?
Because it's the shortest direct distance and we're not using gravity.
So why isn't the shortest one the fastest this time?
Because
There's a vertical plane, not a horizontal.
going down.
Right? The ball isn't traveling at a constant
No,
velocity.
this one's a vertical.
If you're walking,
The
you're
one's
traveling at a
horizontal.
constant velocity, and in that case, the shortest path is the quickest path. You're gonna across the street, right across instead of walking over. But yeah, so that's kind of a comparison.
And this has a direct application to thermodynamics.
Yeah.
If you're taking a coffee to your teacher,
You mean Mr. Audio?
yeah, let's say you're taking to Mr. Audio, and he likes his coffee hot, and that's the idea, coffee should be hot. And he likes it with cream, and he likes it with a lot of cream, 3 creamers in his coffee. And the creamers have come out of the fridge, so they're cold, correct? So, should you get the coffee here and the 3 creams, take them up to Mr. Audio, put the cream in front of Mr. Audio, and then give him the coffee?
Yes.
Or should you put the cream here